Yeah, so integrals, I mean, are the reverse of derivatives, right? You're just going in the opposite direction. So if you saw like the integral of 2x dx, right, that's basically just telling you there's a function whose derivative is 2x. What is the original function, right?
Yeah.
So do you know what it would be here? You kind of have to like bend your brain and try to think in reverse. It's kind of weird.
I mean, just like basing it just on like without like doing anything, I figured it'd be like x squared.
Yeah, it's x squared. And then there's a plus c, which I think we talked about last time, right?
Yeah, you mentioned like putting a plus c at some point in the equation.
Yeah, it's just after you do an integral, there should always be a plus c because for this function, we don't know like was the original function x squared or was it x squared plus 100? Like who knows?
Yeah.
It could be plus 100 because that constant would disappear when we do the derivative.
Yeah, it would make a difference to the answer.
Yeah, yeah,
Yeah.
yeah. So basically, you just did the power rule in reverse, right?
Yeah.
What if I asked you what's the integral of x cubed dx? That one's a little harder. So if
Yeah.
if the derivative is x cubed, then what is the original function?
There was like a formula maybe that like was like a in like normally it's like n minus one, but it's like n plus one.
I was gonna see if you could do it without the formula, but yeah, there's a formula for
Oh,
this
okay.
reason. So if you have x to the m power and you're integrating, then like it's equal to x to the m plus one divided by m plus one plus.
Oh, okay.
I mean, you can see why the formula works, right? If you do the derivative of this, you'll get this, right?
Yeah.
Yeah. So what do you think the answer is going to be here?
Well, if I were to use the formula, it would be
Yeah.
x to the power of four, and then for the denominator it would just be four
Yay, that's the
plus
answer.
c. Yeah.
And you can always check your work by literally doing the derivative of this, and you would get x cubed.
Yeah.
What about if you had the integral of cosine of x?
Well, I mean,
Hmm.
just based off just looking at it, it's whatever like what's the expression that's its derivative is cosine of x. That'd be sine of x.
Exactly, yeah, because the derivative of sine of x is cosine. So yeah, exactly, sine. Oh no, this one is a little bit harder.
Hmm. Yeah, something in particular just has sine of x its derivative. I don't know how to use that formula either on this.
Well, what's the derivative of cosine?
That's a negative sine of
It's
x.
negative sine of x. Okay, so this would be wrong.
Yeah.
Okay, what if we put a negative sign in front? Would it be right now? Maybe.
Yeah.
Yeah, it is right. So if you look actually at a sheet of like here are the different formulas you need to know for integrating, then you would see the integral of cosine, the integral of sine, uh,
Oh.
and those are formulas that you're like expected probably to
Yeah,
put.
just like know off the top of your head.
Yeah. And so in total, there's probably like, I don't know, like 20 different formulas. So there are like properties. It's always weird when you look at math stuff because you're just like, oh my goodness, there's so many symbols on the screen, right?
Yeah, this is like different language.
Yeah, exactly. It's a whole nother language. And like, if you want to be good at math, you kind of have to be fluent in the language of
Yeah.
math. Actually, you don't really have to be fluent, I should say. You just have to be like conversational, maybe. Like you don't have to
Hmm.
know every single symbol probably, but as long as you know like the vast majority of them, then you can get by. But anyway, none of this is actually that complicated. Like this is just telling you that if you have the integral of two things that are like being added, just find the integral of each thing. Like, it's
Oh,
actually not
okay.
that complicated. And you have like a similar rule for derivatives, right? If it was a
Yeah.
derivative, so if you're doing the integral of x squared plus sine x, just integrate x squared and integrate sine x,
And just add them.
and that's your answer. And then this is the same thing, but for definite integrals, like there's numbers for the whatever the bounds or whatever they're called.
Yeah.
If the bounds are the same, the answer is 0
Okay.
because there's no area.
Hmm.
You know what an integral represents, right? It represents area under a curve, right?
Okay.
So if you have a graph and then you have, let's say, some weird curve that looks like this, that's actually not that weird, but anyway, then you could say this here is the area under the curve. We say under the curve, really we mean like in between like the curve and the x-axis.
Okay.
Um, and then let's say this is, I don't know, 8. Let's say it's 8. This is 0 here, of course, right? This here is 0. You're finding the area in between 0 and 8, right?
Hmm.
So you could literally say, if this curve here is f of x, you could say this is the integral from 0 to 8 of f of x. And I guess there should be a dx here or whatever. So that's literally like what the bounds mean on an integral, right? It's like the range in which you're finding the area.
Oh, okay.
So some of these properties here are kind of like intuitive if you think about it that way. So like they say that like the integral from a to a has to be 0. Well, yeah, because there's no area.
Yeah, that makes sense.
Yeah, like there's literally no width to your area. So yeah, it has to be 0. Cool, cool. This is an important property here. You can pull a
Okay.
constant out of the integral, like a constant multiple or a coefficient, whatever you want to call it. You know,
Yeah.
you could do that for derivatives. You could do that for limits. Like that's just like super duper important. Um,
Yeah.
all right. Well, this is the main thing I kind of wanted to show you, right? So these are like and I said there's like 20 formulas that you would know or something. These are the 20 formulas.